Let me introduce our experts today for the Curiosity mission and updates on Mars exploration. So the speaker with us, we have Kenneth Brandt. He's the director of Robeson Planetarium and Science Center in Lamberton, and he has a special guest for us today. So Kenneth?
Good afternoon and welcome aboard on our little trip to Mars today. We're going to go on the back of two very successful rover missions. Because I wasn't going to get a whole presentation about Opportunity, but I've got to mention Opportunity because Opportunity is my fave of all time Mars rovers. Now, future, past, whatever. I'm a fanboy of the Opportunity rover. So we're going to talk about that. But before I do that, let me introduce our special guest from the Jet Propulsion Laboratory in Pasadena, California, Megan Lynn, who's a deputy project manager for the Curiosity rover mission currently. So Megan, thank you for coming this afternoon. We really appreciate you spending your morning with us.
Yeah, glad to be here. Thanks for having me.
So basically, I'm going to do this presentation, but Megan's going to chop in whenever she feels like there's something else needs to be said, or wants to add another detail, or just give you an inside perspective on what it's like to actually work on this rover, which she does, daily. So I'm going to share my screen and pull up. Whoops, there it is, my PowerPoint, and up it goes. And hopefully you're seeing a Mars rover shooting a laser at an unfortunate rock out there on a cliff on Mars, and getting ready to deploy the drill on the robot arm on that thing after it gets done taking some chemistry measurements. All right, so here's the title slide. My email address is here. And if you have any questions that we don't answer during the day, or got any other concerns, or you want more information about the Robeson Planetarium, feel free to email me. I'm also a volunteer with the Jet Propulsion Lab's Solar System Ambassador Program. It's a network of about, I think, 1,200 of us across the world who talk about NASA's missions and missions of exploration. So I'm very honored to be able to do this presentation for you all. So here we go. Whoops. Okay. There. The Opportunity rover landed 17 years ago on Monday past, the 25th of January, our time. It actually landed very late Pacific time on the 24th. And Opportunity drove for 28.2 miles. This is the overhead view from the Mars Reconnaissance Orbiter of where Opportunity is currently. Opportunity is actually about here, and that's where Opportunity will stay, because Opportunity stopped working back in 2019. This is a more global perspective. You can see the size of this crater that Opportunity drove into. It started out here and ends up here, and that's a distance of about 28 miles. If you straighten it out, it's probably a little less than that, but it's a straight line. The total driving distance was 28 miles on Mars, which is the record for driving off-world, and that includes the Apollo astronauts in their roving vehicles in Apollos 15, 16, and 17. So this is by far the furthest driven by any vehicle on any world besides Earth. And Opportunity's most lasting impact may be the interest it generated. And the opportunity to tell the story of Mars exploration to anybody with an internet connection. You can see Opportunity giving a tour of its landing site there, according to Mr. Monroe, who does a comic called XKCD, which this is borrowed from. A Curiosity is looking for the biological potential on Mars. This is the current rover driving around on Mars today. And Curiosity has been driving on Mars now for 8 years plus, 8 and a quarter year and a third of a year, since August of 2012. And you can see the basic mission goals there. And this is a selfie Curiosity's taken with its camera on the robot arm, looking back at the vehicle. And so it's a what's called a mosaic. It's a stitched image of about, I'm thinking 24 or something like that, images that the camera takes, and then they're all smushed together to form one panorama that you're seeing here. Off to the right, you can see Mount Sharp, the mountain next to which Curiosity landed back in 2012. And you can see the atmosphere of Mars is kind of a salmon color. And I'm going to stop and ask, does anybody know why it's that color? What makes it that color?
So if you know the answer, write it down on the chat.
Yes, please.
So Kelly said dust. Sarah said dust.
Okay, that's part of it, definitely, yeah.
Everybody's saying dust. Iron oxide.
Okay, that's the surface. Yep. So the surface is rust, rust or iron oxide, basically. But there's something else going on Mars's air. What's Mars's air mostly made out of? I guess I'm asking here.
Miro said atmosphere.
The atmosphere, yes. What is the atmosphere made out of?
So what is the atmosphere made of? Carbon dioxide?
That's it. Very good. Carbon dioxide. So the air on Mars is very different. And that's one reason why the Perseverance rover is bringing the MOXIE instrument, which is designed to take the CO2 atmosphere of Mars and convert it into oxygen that obviously we could use for all kinds of things as human beings, obviously to breathe it, but you can also use oxygen to make rocket fuel or the oxidant in rocket fuel. So this is a picture taken a while ago. I think it was like 2 years ago. And Megan, maybe you can help me as to when this picture was actually taken. It was taken pretty early on in the mission and looking off to a point where Curiosity was last summer. It's not here anymore. It's actually, I think, up this way since last July when this image was released. But it basically gives you an idea of the perspective for how far Curiosity is actually driven on Mars, which is a long way. And you can see some of the rock, the broken up sedimentary layers of rock here, the remnants of an old lake bed. So these are some of the people working on the Curiosity mission, and you can see they're all sitting comfortably at their desks at home, like us, the most of us who have been working remotely since March. They continue the mission and connect to one another via some kind of video platform, and continue to work on the rover, giving it commands for where it should go to the next sol or day on Mars, and downloading the results that are uploaded from the rover.
Yeah, I can jump in with that one real quick, just because that truly has been our life, just like much of the rest of the world for the last year. And at first, when we were starting to see that this might become a possibility, we were a little bit nervous. Can we leave lab? Can we still control the rover remotely? It was much easier than we expected because we're already controlling the rover remotely. Our hardware is on Mars and we're controlling it from the lab. So it just added one more connection step there. And the team just really adapted to it. And everything's been going really smooth on remote operations.
I have a couple of questions for you.
Go ahead.
Brian wants to know, how fast does it go?
I can take that one. That goes 0.1 miles per hour top speed. And in reality, we usually drive slower because it's a remote vehicle. We have a lot of built-in automation and fault protection so that the rover can look around and take images of its surroundings, and it can even autonomously avoid obstacles if we want. So if we're on smooth terrain and we have great clear pictures, we can drive fast, that 0.1 miles per hour speed, and then we go slower and take smaller steps depending on what's around us, if there's any hazards we're trying to avoid.
And that brings me to the next question from Diego. He said, how many cameras does it have?
Oh, do you know off the top of your head, Ken?
Around 20, somewhere in that ballpark. Might be a few more. I know Perseverance is 23. So it may be pretty close to that number in total, but there's
a wide variety of cameras for engineering purposes versus cameras for science purposes. So some have focus mechanisms. We have some up high on the mast so that we can see obstacles from the distance. And then we actually have some mounted below on the body in the front and the back so that we can see hazards that we're immediately going to approach with the wheels. And then on the end of the arm, that one that takes the selfie is probably one of our most well-known cameras just because of the resolution that comes out in these beautiful pictures like this one you see here.
Mm-hmm. So we have more questions. So because of the surface of Mars that you have rocks, can it jump in case that it needed?
Can it what in case it's needed?
Jump.
Can it jump? The rover can't jump. It moves very slowly. But one thing that it can do is because it has that 6-wheel design and it's what we call a rocker bogie, it allows the wheels to really adjust to the terrain. So we can climb rocks that are bigger than our wheel diameter. And what you'll see is if you ever see this thing in action driving, the top of the rover stays very still while we're driving over very bumpy terrain. So it's just a very well-designed wheel system. And
why 6 wheels and not 4 like a normal car?
The 6 wheels is mostly for that stability and making sure that you're maintaining the flat level while you're driving. It helps us up slopes. It helps us with landing. If you remember, this Curiosity rover landed straight on its wheels. It didn't have anything else assisting it. So take those landing loads and be very secure, as well as help us with driving. And it gives us a lot of redundancy and we can do some unique driving with the 6-wheel combination.
Okay, thank you.
Now, one of the things they can do with these hazard cameras down here at the bottom of the front and the rear of the rover, and emphasize the rear ones, because Curiosity and like Opportunity was another one that could do this, could actually turn the mast around, face the cameras, these 2 cameras back this way, or the hazard cameras here back this way behind it, and actually drive backwards. And a lot of times that became very important when it was trying to, for example, get out of a sand dune that it was stuck in on Mars. So a lot of times they'll actually command the rover to drive backwards and do a significant amount of driving backwards. It also helps to decrease the wear and tear on the wheels. You can see this front wheel here, it's got a hole in it. Mars turns out was pretty tough, is pretty tough on Curiosity's wheels. Fortunately, they seem to be holding up okay. And they'll probably last the life of the mission, we hope. Okay, I'm gonna stop sharing my screen long enough to pull up a video here because I couldn't get the video to load in my PowerPoint. I'm not sure why that is, but I wanted to talk about Gale Crater itself, and this presents an overview of the crater.
In 2012, NASA's Curiosity rover went to Mars to explore Gale Crater, a large impact basin with a massive layered mountain in the middle. How did this strange landscape come to be? And what can its history teach us about the potential for life on Mars? After several years of exploration, here's what we think could have happened. Around 3.7 billion years ago, a large meteor impact blasts out the initial crater, cracking the rock below and leaving a central peak as the surface rebounds. It's a wetter time in Mars history. Groundwater seeps into the new crater, while rivers fed by rain or melting snow also flow, forming a large lake and carrying gravel, sand, and silt. This material keeps building up over millions of years, and as each layer cements into rock, it records a snapshot of the environment that shaped it. In time, the gradual drying of Mars shuts off the rivers, but sediment keeps piling up as sand and dust flow into the crater, deeply burying the deposits laid down in water. Meanwhile, groundwater remains deep below the dusty surface. At some point, winds that once carried sediment in begin scouring it back out. In areas closer to the crater rim, these winds dig all the way down into the ancient lake deposits. And as the heavy weight above is lifted, these layers crack, which helps groundwater flow through and alter them again before they dry out. By about 3 billion years ago, we're left with the basic form we see today. It's in this version of Gale Crater that Curiosity has helped piece together the story. Sediment patterns show a lot of water was present continually over many millions of years, both as persistent groundwater and a long-standing lake with occasional dry spells. Mineral and chemical readings show that water from both the lake and subsurface was friendly for potential microbes. Drill samples from the lake bed show key elements, organic molecules, nutrients, and energy sources that microbes could have used. Water flowing through underground fractures could have supported life even in deeply buried rocks. And the composition of some layers makes them good for preserving potential signs of past life. Taken together, the evidence points to Gale Crater, Mars in general, as a place where life, if it ever arose, might have survived for some time. With our primary mission fulfilled, we continue exploring, uncovering the history of Mars and learning more about how and where future missions can search for the signatures that ancient life may have left behind.
It's a really good point that the video brings up here about now that the primary mission is done. This thing was supposed to last for 2 Martian years, or two years, I think, 1 year on Mars. And it's lasted like 3 times longer than that and counting. Opportunity lasted like 55 times longer than its lifetime, engineering lifetime in 90 days. So one reason why it's my fave. But this mission is yet another example of really, really, really strong engineering and design, because this thing is put together, and my hat's off to you, everybody out there at JPL, every time, because it's just amazing. These things are built tough, and they're built to withstand the environment on another planet. It's completely different from Earth, of course, and it's just really fascinating to me that this mission continues to go day after day, long after it's supposed to stop, and it's just a really good thing. And I like NASA's rule: if you've got a working spaceship somewhere, you keep feeding it money so it keeps running. Because it's a lot cheaper to keep a mission running than to start a whole new one. I mean, you can do the new ones in addition to that, but you got to keep the ones that are already going. And they've got a pretty good policy about doing that, which is I think very positive. Okay, I'm going to go back to my screen here somewhere. There it is. Okay. There. Okay. Okay, so this is Mount Sharp here, up in the distance. Really tall mountain. Mount Mitchell in North Carolina would be this little lump right here along the way up. So give you an idea of relative size. And this is where Curiosity is driving now. It's on its way into the sulfate unit. Megan, is it already in the sulfate unit, or is it still on its way there?
So we're in what we call the transition. So the clay sulfate transition, which all of the geologists love to study this transition to see how we move through the different layers and what causes the change, because that tells us a lot about the past history of Mars.
Okay. So there's all the places it's been and the places it's going. And they ultimately want to end up in this river valley up here. Is that right?
Yes, that's where we're headed. So we do strategic routes that kind of plan our path out for a couple of years at a time. And that's where our current strategic path ends. And we're coming up on a new cycle where we'll start to look 2 to 3 years out in the future again and see what's next to come for Curiosity.
Okay. So this is the drive map as of about 80 days ago, or 80 sols ago. But it's the most current one I could find. And it shows you the Bradbury landing, which I thought was significant because, to honor Ray Bradbury, the science fiction author, who wrote extensively about Mars. And it seemed really fitting that NASA would name this spot. The cool thing about being explorers, like Megan and company, is when you go to places, you get to name them. You get naming rights. And so all these names are from mission team scientists, or engineers, I think. That will come to a place and say, hey, that reminds me of this rock unit on Earth. Let's name it that. They were talking about spending a fair amount of time in Scotland, if you will, and some Scottish terrain. And then they're moving into France. So now the names of objects get French names instead of Scottish ones, excuse me. So So that's the drive map. You can see it's not a straight line by any stretch. They're trying to drive. Doesn't look like you can drive over this. You know, it looks too steep. So they had to drive
That's
around.
actually all active sand dune, and we couldn't drive through the soft sand without risk of getting stuck there. So you can kind of see all the dark, more blackish areas on here is sand, which is treacherous to drive through. So we were getting just as far away until we found our first opportunity to cut in and start climbing up the mountain.
Gotcha. You guys learned from Spirit and Opportunity. The hard way, unfortunately, for Spirit. But yeah, but so this is some of the chemicals that are found in the soil, and mostly my zoom settings are impeding my ability to see what's up here. But this looks like the chlorobenzene.
Yes, that's chlorobenzene. So it's the first organic that we were able to detect. And this is showing the 4 different drill holes for comparison, because whenever you do an experiment, you want to back it up with data to make sure you're seeing something for real. So in comparing how much we've actually detected through the instruments from these 4 holes, Rocknest, that's a scoop, John Klein, and then this green one in Cumberland, you can see that is a real signal and that it's well beyond the noise level. So that all helps you to prove your point whenever you're detecting something new on Mars.
The other thing I wanted to point out is the color of the drilled material. And that once you get inside the rock, it's a very different color than outside. It's like when you go rock hunting here in the mountains of North Carolina, for example, a lot of times you'll pick up a rock and it'll be kind of dirty brown looking. And then you take your rock hammer and break it open, and it's white and black in the middle, or it's got crystals, blue crystals in it or something, because the inside hasn't been oxidized. Like the soil here in Rocknest is pretty clearly mostly iron oxide here. When you get down in here, you've got another material altogether. It's not that iron oxide rust covering anymore. So the drill is a very, very important instrument. The drill and the laser are 2 of the ways that Curiosity can get up underneath the rust to get at the real rock story underneath, to find out what that's about. So Curiosity shows us that you can see the abundance of all these chemicals in in a particular soil sample here. Phyllosilicate is a kind of clay, and you can see all these different chemical signatures for elements. And when you start mashing them together, make things like amino acids and sugars and the other chemicals that we're familiar with when we talk about life. So the lake bed at Yellowknife, shows you that life could have formed there, because everything that was needed was there. Including an energy source. Sulfur is a really good energy source for moderating chemical reactions in living things. And so it could be, that could be the energy source for a primitive life form on Mars. So the hard part is we don't know for sure that there's actually life in that spot. Got a lot of really nice suggestions and hints, but nothing concrete yet. So what I just said, basically.
So if you don't mind, I'm getting a lot of questions from the chat.
Okay. Oh, go ahead.
So I would love to ask you some. So in general, about the geography of Mars. So what is the percentage of the surface that is volcanic rock in Mars?
An overwhelming amount of the rock on Mars is volcanic, because there's a lot of volcanism that happened on the planet. But the more they explore, the more it seems like we're finding sedimentary rock.
Mm-hmm.
So that's starting to balance out. What you're missing in a lot of cases is metamorphic rock. Now you have some rock alteration, like in veins, where water percolates up and modifies the rock that percolates through. But in general, it's either sedimentary or igneous rock or volcanic.
Mm-hmm. And with this type of soil, you can find plants, or it is possible just to make plants grow?
Yeah, if I remember right, the soil that most of Opportunity drove through was really good if you wanted to grow things like tomatoes. You know, it's pretty acidic soil. So you'd have to moderate a little bit and then you could plant tomatoes in it or something like that. The soil where I think Phoenix landed was really good for growing broccoli and other basic garden vegetables. So it was a basic soil as opposed to acidic. So I'm not sure about Curiosity though.
Mhm.
We're right in the middle of those two with Curiosity. We have a very neutral, not too acidic, not too basic.
Okay.
Okay. And I have some guests that they want to go on vacation there, so they are asking about the weather. So do you have seasons in Mars or not?
Yes. Mars is, let me get down to the slide here. Mars has 4 seasons like Earth does, depending on where you are, of course, will determine what season you're in. For example, I think Curiosity is just south of the equator on Mars. Is that right?
Yep, that's right. We're coming up
Okay.
New Year, actually. Early February is New Year for the rover.
Oh, okay. All right. So it's experiencing then wintertime, or as close to winter as it's going to get, barely
Yes,
south.
we're starting to get colder. I'd call it fall, or I guess autumn for your chart, where we've
Okay.
definitely out of our summer turn. We're turning colder. We're starting to adjust all of our temperature predicts.
Okay. So yeah, and Curiosity also has an instrument on it called META, and META takes daily weather measurements of the temperature, the barometric pressure. I'm not sure about humidity, but basically gives you a daily weather report from Mars. So, and Perseverance also has a weather instrument on it that will be measuring daily. But I brought this slide up because I wanted to show you that methane was something that was discovered where Curiosity was. It's the first time of surface detection of methane has happened. And it's happened now over a couple of Martian years, 2 or 3 Mars years, where these seasonal variations of methane occur, where you have a slight spike here in summer, and then a decline in the concentration of methane in the air in the winter. So it's pretty interesting that the methane level changes seasonally. And of course, there's a couple of possible explanations for that. And they could be anything from actual microbes releasing methane like they do here on Earth, to the combination of water and olivine, a mineral that's pretty common on Mars, forming into methane using the radiation of the sun.
So can you tell us the equivalence on densities of rocks, soils on Mars versus Earth? There's any rock that is similar?
In general, Mars is slightly less dense than Earth, but the rocks are basically, they're pretty close analogs to one another in most cases, I think. Megan, am I right on that one? Or?
I can add for development too, the engineers work very closely with geologists who pick out rocks that they think will most closely match the landing area. So we had some sandstones that we would practice drilling with, all the way up to something as hard as a basalt rock. And we haven't encountered anything as hard as those basaltic rocks yet when we've gotten there. So yeah, everything has been a lot less dense and fairly friendly to drilling what we've gone through with Curiosity so far.
Yeah, it's kind of cool. There's a whole yard at JPL in the back of the compound there. It's on a hill and it's called the Mars Yard, and they'll actually put in different types of rock and simulate driving on that rock. Like they make cliffs out of what is it called, flagstones that I believe they acquired from a hardware store to actually put up a cliff kind of like the cliff that Opportunity at that time was trying to climb on Mars, and or go down into, actually. It's trying to go down into, I think, Victoria Crater. But yeah, so that's there's several different ways the methane that they're observing on Mars can form. The one that's most intriguing would be the organic possibility or the life possibility. But again, nothing concrete, no actual detection of the microbes that would cause these outgassings. So this is kind of a geologic overlay of the rock units that Curiosity could be going into. And I'm thinking Curiosity is down here somewhere still, at the bottom of this image.
Not quite that far. So we're kind of in the orange area that says clay and sulfate right now.
Oh, okay.
And a large sand dune right there, which is very familiar to me because we've been skirting around that for the last couple of months right now, just to try to get to the sulfates. So we're somewhere in between that clay and sulfates. We've just gotten beyond that sand patch and we're starting to the sulfate.
Oh, my bad. Curiosity's driving this way.
Yep.
From
the top
left
down.
to right. Okay. I was completely backwards. Okay. So uphill is down the bottom right here. I guess that would make sense with the flow of the stream channel. Hugo, are there any other questions that are coming in?
Yeah, but I'm going to wait for the next break because I want to see what have you prepared for us.
Okay. And again, more of the same. There's the stream channel again. Mount Sharp is up here off the camera to the right, lower right. And a quick note about the night sky on Mars. This is just after apparent sunset. We see two bright objects in the sky here. What do you think these two objects are? And you can put your answers in the chat if you'd like. So we got this object here, and then this brighter object down here. What are we looking at here?
So what do you think, guys?
Yeah, what do you think? What do you think we're looking at in the Martian
They
night sky?
said moons of Mars.
Nope.
No. Saturn, Mars,
Nope.
Earth and Moon, Earth and Jupiter. What about
Okay.
the rubber lights?
Earth, yes, but this one we're still waiting on that one.
Venus?
There you go. That's Venus. So Earth and Venus are pretty close to each other in the sky here in this picture from Mars. And you can see Venus is not nearly as bright as it is as seen from Earth, because Venus, of course, is much further away from Mars than it is from Earth. And so it's much dimmer, as we see it. But there's Earth there. And if you look really carefully, there's two dots there. There's the Earth, and the Moon is right there, just off to its right. So you can actually, if this was just a hair more in focus, you would be able to resolve both the Earth and the Moon in this image. And of course, my last slide is this one, which shows a sunset on Mars, or an apparent sunset on Mars. Anybody know why I say apparent sunset?
So write your answer on the chat.
Yeah, throw your answer in the chat, please. Why am I saying apparent sunset? Or why am I putting sunset in quotes here?
So they are very direct. They said no.
Okay. Well, let me ask this question. Is the sun actually setting?
Huh.
Because that implies motion. So is the sun moving here? When you watch a sunset in time lapse, is the sun the one that's moving?
No.
No, it's the Earth, or in this case, Mars, that's actually rotating. And that causes that motion that you see in the sky we call sunrise and sunset. So your weatherman is lying to you. No. But you can see the sunset on Mars looks very different because of the air and how it scatters light. In a case like Earth, this would all be orange and yellow and red and everything. And on Mars, we go in various shades of purple and blue because of the carbon dioxide in the air.
That's interesting.
All right. So here you go. This is a good time for more questions if they've got them.
Well, if you want questions, I have tons of questions.
Okay, good.
So,
Bring them on.
So Leonie wants to know, do the rover feel the Mars quakes?
That's a question about InSight. That's another mission that landed on Mars in 2018, I think, called InSight. And that's a lander and its job was to find Mars quakes. And it has found evidence for a lot of small Mars quakes, nothing really big, you know, no real shakers, you know, but a lot of little ones.
And
and
yeah.
InSight are very close to each other. So in the sense, the rover probably did feel what InSight felt just based on their location to each other, but we don't have any sensors that are sensitive enough to detect it. And we looked when they found, now we had a time point for when we could look in the data, we could see if we could tease anything out there. And we'll keep looking if they find anything stronger, just to see if we can ever detect it. But nothing that our sensors can pick up on the Curiosity rover.
Mm-hmm. So Gabriel wants to know, why does it have a laser?
Why does it have a laser? Woohoo! The laser is a piece of equipment I would like, because as a rock hound who's out there looking for rocks, like there's a mine called the Crabtree Emerald Mine out in Little Switzerland, North Carolina, and you can actually find emeralds out there. Well, it would be really handy to have a rock laser that you could shoot across the mine at different piles of rocks and analyze them from afar, so I wouldn't have to waste time walking over there and smacking all of them with a rock hammer to find out if there were emeralds in them. Because the rock laser, what it does is it shoots a hole in the rock, and then the vapor coming off of the hole is analyzed by an X-ray spectrometer. And the spectrometer is looking for patterns of lines that signify different minerals. So you can actually tell what the rock is made of, and you can do it from a distance of up to 20 feet away. So if you got a rock that's, say, up a cliff 10 feet tall that the rover cannot climb to get to with the drill or anything else, you shoot it with the rock laser, and you can get a pretty decent signature for what chemicals are in the rock.
Mm-hmm. So another question from Chelsea. Does the dust on Mars ever mess with the way the rover works?
It depends.
Okay, I'll definitely let you handle that one.
I was going to say I could let you answer for Opportunity. So the interesting thing between
Definitely.
Opportunity and Curiosity is Opportunity was solar powered. So it had solar panels on its back. And as the dust kind of settled onto it, it would get less and less power to recharge its batteries every day. And then it would get lucky every once in a while, and a windstorm would come and blow the panels clean, and then it would have more power than the rover knew what to do with. Curiosity doesn't have that problem, because you can see on the back of the rover there, first of all, there's no solar panels, but the back we have this, it's called an RTG. It's a radioactive thermal generator. So there's a small radioactive source on board that decays, and we take that heat energy and we turn that into power for the rover. So we're not dependent on sunlight at all, which made it so that we could do some really cool observations during the dust storm. When the dust storm's blocking out all the sun and light, we don't have to hibernate as a rover. So we could make some good observations of dust storms.
But you can see on the deck of the rover here, the dust buildup over time. You know, so it's definitely getting dustier over time.
Mm-hmm. And talking about the solar panels, that brings me to the next question that Henry has is, does the rover run out of battery?
Probably not for about 20 years. I think the RTG's got about 20 years of life left in it, or about 10 Mars years left of life in it. So
that might be a little long of an estimate, but we are starting to get power dependent now, because we have to send power to be able to heat things. If we can't heat our actuators, we can't move them. So winters get a little bit tight where we have to send power to everything. And then summers we're back with a lot more energy, and we can sort of drive and move unrestricted now. With energy though, we carefully balance our batteries, where kind of like your cell phone, you don't want to always keep it plugged in all the time. You don't want to always be draining it to nothing. We try to charge it up most of the way and then discharge it pretty good over the course of a day, and then charge it up overnight again. So we go through these recharge cycles on a daily basis with the rover. And then, yeah, it'll just, as that power source degrades a little bit, we won't run out of battery. We can keep filling up the battery, but it'll take longer to do so. Maybe it'll take 2 nights of sleeping before we can do a full day's activities again. We go on.
Okay, so now I have a situation. So Isaiah and Leslie, they put us on the worst situation. What happens if it falls or the Curiosity blows a tire?
We can't blow a tire because there's no air in our tires. So that's one benefit. The Curiosity wheels have been talked about quite a bit lately because you can even see in the image that they look pretty beat up. And we analyzed that right when we landed because the wheels were getting a lot more damage than we had anticipated. And we actually performed about a year or two's worth of testing here on Earth of the wheels to see how do they fail if they encounter certain types of rocks? What does the damage look like? And having seen some of that data, even though they look pretty beat up from an engineer standpoint, I don't think we're going to have to worry about the wheels. They're going to last the course of the mission.
And what that happened, I'm not sure which of the rovers, either Spirit or Opportunity, had a wheel freeze up on it, just stopped working altogether. It wouldn't turn. And so that's when they started driving backwards. They actually turned the mast around and used the back hazard cameras and just drove backwards and dragged that wheel along behind them, so to speak. So the wheels do fail. I mean, they can fail, but there's usually a driving solution that will allow you to drive with at least 5 wheels working. But once you get more than 2 or 3 wheels that don't turn anymore, you're kind of stuck.
Yeah, that's the benefit of the 6-wheel design, and each one has their own individual drive actuator, and all 4 corners have the ability to turn independently. So if anything were to happen to an actuator, which is what happened with the Spirit, it would be limited to just that wheel, and we'd be able to work around it with the others.
Mm-hmm. So Leonie has a question related with the wheels. So she wants to know if she can see them like the wheel prints, see them like you can see the footprints on the moon.
Yeah, that's a great question. We do, and we actually use them on the mission itself. So we have a capability that's called visual odometry. So when you're driving around on Mars, you think that we want to know how far we've gone. Maybe we're trying to get to a certain target, but sometimes you'll get on some sand and the wheel will slip. So you don't actually make forward progress, even though you're turning your wheels. So what happens is when we're driving through that sandy terrain and we are leaving imprints, we have a high risk of slipping. So we'll take pictures of those imprints, and there's a unique design on every wheel. So once per rev, it stamps that footprint down on the surface, and we can measure the distance between those. And if that distance is getting closer and closer together, it means we're slipping a lot, we're not driving. And we actually the rover can fault itself and say, I'm slipping too much, I'm gonna stop right now. And we did that once in the mission where we were driving into sand. It got too much slip, and the rover autonomously stopped and waited for ground in the loop for us to take a look and see what's happening. And we decided to reroute. We backed out of that and we went a different direction, all because we could take a picture of our footprints.
And you can see in this image here, the selfie, in the background, you've got some tracks going off in the distance here. So there's visual evidence of these footprints. There's a really iconic image for me of Opportunity with the footprints actually going off in the distance and forming what artists call the vanishing point, where the 2 parallel lines actually appear to merge in the horizon. So it was driving basically in a straight line for several hundred feet at least to form that vanishing point image.
Mm-hmm. So Diego wants to know, how far has it been driven since it landed on Mars?
Just over 15 miles.
15 miles.
Just over 15 miles, yeah.
Okay, and the Curiosity is the rover that has the bouncing landing?
No, Curiosity landed using a sky crane. And so the sky crane was a set of rockets and a set of cables that lowered the rover down gently onto the ground on its wheels. So when Opportunity and Spirit landed, you had to unfold these landing pedals and deflate the airbags and everything. And then Opportunity had to actually deploy the wheels and then roll off. It was like, I think it took them about 3 weeks to get all that done back in 2004. But here it was basically the next morning, put the mast up and start driving. They could go basically right away.
Mm-hmm.
Start driving on Mars. Didn't have any prep work to do.
So as every time that we see these pictures, in our mind, we are thinking about a giant machine. How big are these rovers? They are big, like a car, like a truck?
Yeah, like a car, like a mid-size SUV, basically.
I like to compare Curiosity to a Mini Cooper because when we were testing the back shell to make sure it was big enough, the company that built it actually put it over a Mini Cooper car to show that the dimensions fit. So it's when when the mast is stowed down, it's about the size of a Mini Cooper.
Yep, the tires are the same, almost the same size tires you would use in a small automobile. So they're pretty big tires. And the machine stands 8 feet tall from the bottom of the wheel to the top of the mast. So the images here are what a tall astronaut would see on Mars. When you're looking at these panoramas taken by these two cameras here. I forget the name of the camera, mast cams up here.
Yes, those are the mass cams.
Yeah, those are the ones that provide the really, really high res panoramas that you get from Curiosity. You know, we're talking several billion pixels worth of data.
And this is the tricky question with all those images. Have you seen weird activity?
I'll definitely let you handle that one, Megan.
We haven't seen anything weird in terms of are there aliens running around Mars? Nothing that we've captured. We do dust devil surveys sometimes where we'll just look off into the distance and take a series of pictures. So we have been successful in capturing videos through these still frames of dust devils going through that will look off into the distance. We had early in our mission, the public picked up on a sort of shiny piece of debris that we drove by, wondering that can't be natural, and we drove by it. And that's true. We looked at it and analyzed it. And because we had that sky crane landing, part of what we have to do is we have these pyro actuators that have to blow to make some breaks in the hardware so that that whole sequence can happen, and that can create some debris. So we just came across some of that later on as we were driving out of the landing area. So I'd say that was probably the weirdest thing that we've seen that we had to try to figure out and explain for the public to let them know what we drove past.
Hey guys, sorry, not ET for now. So we have to wait. So I have another question from Marianne. How fast does the data come back?
There's a time lag, and that time lag depends on the distance between Earth and Mars. It can be anywhere from, I think, 3 minutes to 21. Megan, are those numbers ballpark right? Or
Yep, that's the one-way light direction at min and max.
okay. And of course, radio waves, for a lot of people don't understand, radio waves travel at the same speed that light does. And so the radio waves will take 3 to 21 minutes. It's one reason why the rover has to be able to make its own decisions when it's driving. And like the example of stopping in the sand dune when it felt itself slipping too much. If it had to wait for earthbound commands to tell it to slow down or stop, it would be way too late. It would already have driven into the sand dune and been stuck. But in this case, the rover has cameras up here, navigation cameras up here and down here at the base, in the front and back, and it can actually make a 3D set of images that the computer then processes and develops a driving map that it can use to drive safely from point A to point B, or stop if it gets to a point where the slope gets too steep or some other design parameters that are built into the software. It automatically knows to stop and wait for direct. Then it will stop and radio back, hey, give me some directions here. Let me know what to do.
Yeah, a lot of people think that driving the rover is more like you're joysticking it around or you have a video game controller and you're driving it. But because it could be up to 20 minutes back and forth for each data, you can't do that reasonably. So what driving the rover more closely looks like is coding a computer program. So you're writing in, take a step 10 meters forward, take a picture, and then once you get beyond the images that you can see is when you're letting the rover make these more autonomous decisions on its own. And we'll plan from 1 day to sometimes up to 3 days at a time, so that we can take weekends off and then look at the data on Monday when we come in the morning and make sure that the rover made progress and everything went according to our plans.
Speaking of taking the weekend off or showing up to work on Monday, if you're here in North Carolina and you get up at 8 o'clock in the morning and you go to Curiosity's multimedia page and you pull down the raw images, the images taken yesterday on Mars, you might see them before the science team sees them or the engineering team sees them. So you might be the first person or one of the first people to actually see that image, depending on when it gets downlinked back to Earth. Because a long time ago, back in the Spirit and Opportunity days, a decision was made when data comes down, it basically gets trunked out in 2 different pathways. one to the mission team and one to the public. Basically gets put up on little thumbnails and put up on the internet. So so you could, in fact, follow along with curiosity every day if it's something you wanted to do. And a lot of times you would be beating the scientists to the punch, so to speak.
Okay, so
Because they show up at 11 o'clock our time, right?
So we're getting close to the time. So I want to wrap it up with one question for you both. Is we have young students in here, so they want to know what degrees do you and the team have, and what is the best background? So tell us.
Well, Megan, you're actually working on this thing. You can go ahead.
Sure. So my personal background, I have a bachelor's in mechanical engineering and then a master's in engineering. And I started off on the design side of the rovers and doing some of the early testing and some plans for how to build it. And then I moved over into the operation side as I learned how these rovers are built. I was able to apply that to how to actually control them on Mars. You'll see a lot of engineers. You'll see some computer scientists right now is getting really popular because once we're landed, you can't touch the hardware anymore. Everything that you have is the data coming down and how you process that data to learn what the rover is doing. So that's very common around me right now. And scientists, because those are the ones who are actually analyzing the data to see what is this actually telling us about the history of Mars. So we have a lot of geologists and chemists and astrophysicists right now who work very closely with the team to help interpret the data, but also to help us decide where we should go with our strategic route, because they want to go and explore these things because they'll tell them the most about Mars.
And we're figuring out what to study, and more important, where to study. You know, just work as hard as you can. You know, honestly, just work as hard as you can and look for the lucky break. You know, getting the opportunity to intern at JPL. If that ever happens to you, pack your bags and go. Okay, tell everybody you left later. Okay, go to JPL and work there with them. That's one of the surest ways. Megan, you did that, didn't you? You interned at JPL before you started here?
I was an intern, so I did 2 co-ops. I went to Northeastern University, and what we do is we go to school for 6 months, and then you go and you do an internship for 6 months, and we do 3 cycles of that. So I did 2 of my 3 internships at JPL. So I was from Massachusetts, and I came all the way to California to do my internship. And I actually had found this out and was able to interview for the internship through going to a Society of Women Engineers conference. And NASA and JPL does a lot of outreach there, and they'll collect resumes, and they'll go to career fairs. So for all of the technical conferences.
Yeah, that is great. So let me share my screen. Okay. Because sadly, we don't have more time. So I wanted to thank you, Ken, for being with us. And of course, Megan, thank you very much for this short
Thank you.
call. And thank you, the NC Space Grant, for being our sponsors. Thank you to all the members of Friends of the Museum for their support. And of course, thank you all for being with us today. And before we leave, I want to tell you that Ken is going to be with us again tonight. I think they said around 5, to talk about the next mission to Jupiter. So from Mars, we're going to jump over Jupiter. And remember that we have tons of programs and activities during this week, so you have to check our website. And of course, you can be part of our astronomy days with one of our exclusive shirts and hoodies. So check them out at the same link. And last but not least, your opinion is very important for us, so please follow the link to our survey and tell us how we are doing. So with this said, thank you, Ken. Thank you, Megan. And thank you, everybody. And see you in another program. Happy Astronomy Days, everybody.
Yay, happy astronomy days.